Welcome to the Explainer. Today, we're going to talk about a fundamental programming concept that can make your code, well, ridiculously faster. We're talking about the difference between hitting run and going to make a coffee versus getting an answer instantly. Okay, let's just jump right in with a classic problem. Picture this. You've got a massive list of numbers. I mean, huge. And someone starts firing questions at you. Hey, how many 5s are in there? What about 27s? How many times does 99 show up? You need to answer. And you need to answer fast.
Now, the first thing that probably pops into your head is the most obvious way, right? For every single number they ask for, you run a for loop through the entire list from start to finish, you keep a little counter, and you just add them up. It's simple, it's logical, and you know what? It works.
But what happens when that list has, say, 100,000 numbers, and they ask you 100,000 questions? Suddenly, that simple little loop becomes a monster. You're scanning the whole list once, twice, 100,000 times. The time it takes it explodes.
In fact, for a big enough problem, this brute force approach could take around 100 seconds to run. And in the world of computing, 100 seconds is an eternity. I mean, your program would time out on pretty much any online platform. There has to be a better way.
And of course there is. The solution is a really cool technique called hashing, and it is a beautifully simple idea that completely flips this problem on its head.
So here's the core idea. Instead of doing all that work in calculating the answer every single time someone asks, hashing is all about doing the work once, up front. You pre-calculate all the answers, you store them somewhere smart, and then you can just grab them in the blink of an eye whenever you need them. It's really just a two-step dance. First, the pre-computation. You just make one single pass through your entire list to build a frequency count for every number. We can store this in something called a hash array. Then comes step 2, fetching. Now when a question comes in, you don't loop at all. You just go directly to that number's spot in your array and boom, there's the answer, instantly.
And this is really the magic of it. Think about that shift. Instead of taking n steps, where n is the size of your list, for every single query, you take n steps just once. And after that, every single query is just one step. It is a total game changer for performance.
Okay, so this hash array thing sounds amazing, right? But it does have a hidden weakness, a bit of an Achilles heel. What happens when the numbers themselves are massive? To use an array, you need a slot, an index, for every possible number up to the biggest one. So what if your list has a number like, 1 billion?
And that's where our simple method completely breaks down. You can't just declare an array with a billion slots. You'll probably get a segmentation fault, which is just a fancy way of saying your program tried to eat up way more memory than it was allowed to and crashed. Most systems will only let you create an array up to about 10 million elements or so. So our brilliant solution has a flaw.
So what's the fix? Well, we don't have to throw away this whole idea of hashing. We just need a better, smarter tool for the job. And that tool is a data structure called a map.
The easiest way to think of a map is like a dictionary. You have a key, which in our case is the number from the list, and a value, which is how many times it appears. And here's the magic trick. A map only uses memory for the numbers that are actually in your list. It doesn't need a slot for every number from 0 to a billion. If you only have 50 unique numbers, it only makes space for 50 pairs. It's incredibly efficient.
Now, in languages like C++, you usually get two flavors of this. You've got your standard map, which is great because it keeps all your keys sorted and has a very fast, very reliable lookup time. But then you have its cousin, the unordered _map. This one doesn't care about order at all, and because of that, it's usually even faster. On average, it gives you what we call constant time lookups, which basically means it takes the same tiny amount of time to find something, whether your map has 10 items or 10 million.
So that begs the question, right? If the unordered map is the fastest, why on earth would you ever use the regular one? Well, it all comes down to a really rare but important worst-case scenario.
You see, this worst-case scenario is caused by something called a collision. An unordered map uses a special function, a hash function, to figure out where to store everything. A collision is when that function accidentally tells two different numbers to go to the same exact spot. Think of it like a code check at a party, where the attendant gives two different people the same ticket number. It causes a little confusion, and it takes a bit of extra time to sort out. And that little bit of time can slow things down.
And that brings us to the final trade-off. Let's break it down. For average speed, unordered map wins, hands down. It's the fastest. But look at the worst case.
If you get unlucky with a ton of collisions, it can actually get really slow. The standard map, on the other hand, is Mr. Reliable. It's always consistently fast, no matter what. Plus, as a bonus, it keeps everything sorted for you.
So what's the real-world advice here? What's the takeaway? It's simple. Always start with an unordered map. 99.9% of the time, it's going to be your fastest option. But on that super rare occasion that your code is still too slow or times out, you now know the secret. You might be hitting that worst-case collision scenario, and you can just swap it out for a regular map as your super reliable backup plan.
You know, this whole journey from a simple loop to a smart map really proves a point. Choosing the right data structure isn't just some tiny little optimization. It's a fundamental shift in how you solve a problem. It's literally the difference between a program that takes 100 seconds to run and one that feels instantaneous. It just goes to show you, really understanding these tools isn't just helpful, it's a programmer's superpower.